Hello, my name is Thomas Stone, and I'm a second-year master's student in Computational Science Center at SDSU. My advisor is Dr. Margarita Capriotti from the Aerospace Engineering Department. My research is on using physics-informed neural networks for ultrasonic guided wave propagation in solid media. Non-destructive evaluation, or NDEs, encompasses techniques that aim at assessing the state or integrity of a structure without altering its properties. Ultrasonic guided waves are an advantageous NDE method which uses particular ultrasonic bounded waves propagating objects with specific geometries that are typically found in aerospace, civil, and biomedical structures. In Figure 1 we can see an example of such waveguide structures, such as the hull of a ship or aircraft's fuselage and wings, that can be inspected with ultrasonic guided waves to determine there are no damages. In Figure 2 we see an example of an ultrasonic guided wave testing for defect detection in a structure. Ultrasonic guided waves offer many advantages such as long range and entire cross-sectional inspection. In Figure 5 we see a simulation of an ultrasonic guided wave propagating in 2D over time. But ultrasonic guided waves present inherent complex behavior such as dispersion, which distorts the wave shape as it propagates, and having multiple wave modes, which makes it difficult to select and understand the response of the wave interacting with defects. Figure 4 shows the representation of such dispersive multi-mode behavior for the phase velocity of an ultrasonic guided wave in plates over the frequency range. Figure 6 shows a typical wave form where multiple modes are present, making signal interpretation very challenging. Modeling ultrasonic guided waves is crucial to address these challenges and understanding how to better use and interpret ultrasonic guided wave propagation and scattering. Analytic solutions do not exist for ultrasonic guided waves in complex material and structures with discontinuities. There are several numerical methods to model ultrasonic guided waves, such as finite difference or finite element schemes. These methods can be computationally expensive when simulating ultrasonic guided waves over a broad frequency range and interacting with complex geometries. Hybrid methods, such as the global local method, try to address this issue, but other approaches may be sought. This project explores a new method for simulating ultrasonic guided waves propagation with physics-informed neural networks, also known as PINs. PINs are a new type of machine learning method that uses neural networks to solve partial differential equations. This is done by inputting a random sample of coordinates for the time and spatial dimensions into the neural network. The neural network then performs a forward pass to obtain a solution to those points. The physics equations are used to evaluate how well the network performs. This is also known as the loss function. The loss function then updates the network to correct the areas that have performed poorly. The advantage to PINs is that we do not require obtaining data to train the network, and we can also use less data as PINs will use statistical inference to approximate solutions on points that were not trained on. Literature shows that fully connected neural networks tend to bias towards low-frequency solutions. In order to address this, we implement a new neural network architecture known as Fourier neural networks. Fourier neural networks will encode a Fourier mapping for the input layer to take advantage of solutions in Fourier space and output approximations to the inverse Fourier transform. In this case, we are modeling the wave propagation solution to the Helmholtz equation in a 2D rectangular structure as shown in the scheme and the equations on the slides. We set the boundary condition to have displacement equal to 0 for the upper and lower sections of the rectangle, which will cause reflection in the propagating wave. On the left vertical boundary, a second mode sine wave is imposed, where the height is the same length as the wavelength, and the right boundary is open. In addition to our boundary conditions, we are given a frequency of 816 kHz, a length and height of 500 mm, setting the solution to converge over 100,000 iterations. Figure 13 shows an animation of how the network converges to a solution over each iteration. We see figures 14 through 16 that the loss improves over each epoch. Going forward, we will be looking into improving our accuracy as the number of iterations to converge to a solution. Lastly, we will be moving forward to using an ultrasonic guided wave geometry, as this is currently modeling 2D waveguides. Here's a list of references that were used for this research and presentation. I want to thank SDSU, Dr. Jose Castillo with the CSRC, and our collaborators at UC San Diego. Thank you for watching my presentation, and I look forward to meeting you at ACSESS.